Students, in this video I will discuss about circular motion. If a particle moves such that its distance from a fixed point remains constant, the motion is called circular motion. The kinematics of circular motion with constant angular acceleration is similar to the kinematics of rectilinear motion. Kinematic equation of circular motion around a fixed circle with constant angular acceleration, assuming the initial position theta naught equals 0, is written as omega equals omega naught plus alpha t, theta equals omega t plus half alpha t square, omega square equals omega naught square plus 2 alpha theta. Unit vector along normal and tangent to the circular orbit or path. The figure shows a circular orbit with center at O, and consider a point P on this circular orbit located at angular position theta. Let's find unit vector along tangential and radially outward direction at this point. Using geometry we can obtain ET cap, which is a unit vector along tangent direction, equals minus sin theta I cap plus cos theta j cap, and En cap equals cos theta I cap plus sin theta j cap. This is the unit vector along the radially outward direction, or we can say normal direction. These two unit vectors are perpendicular to each other. These vectors are very useful while writing the dynamic equation of circular motion. We write the equation considering the component of motion variable in these two mutually perpendicular directions. The z direction is perpendicularly outward of the paper and the angular position is in z direction. Now let's define the angular velocity and angular acceleration. Angular velocity, represented by the symbol omega, is defined as time rate of change of the angular position. So mathematically we can write omega equals d theta upon dt. The angular acceleration alpha is equal to d2 theta by dt square, or it will be equal to d omega by dt. So we can define angular acceleration as time rate of change of the angular velocity is called angular acceleration. Tangential velocity. A particle executing circular motion has its direction of instantaneous velocity along tangent to the circular path at the point where it is located. So we can write vector v equals vector omega cross vector r. Since the direction of angular velocity is perpendicularly outward of the paper, its direction will be in anti-clockwise sense. We can write tangential velocity as vector v equals v et cap. Acceleration. The acceleration of particle at any instant of time t is defined as the acceleration vector equals dv upon dt. But we also know that the velocity v, which is in tangential direction, equals vector omega cross vector r. Therefore, if we differentiate the expression of velocity vector v, we will get the acceleration vector equals omega cross dr upon dt plus d omega by dt cross r, which will simplify to minus omega v en cap plus dv by dt et cap, which again will be equal to minus omega v en cap plus alpha r et cap, and this will be equal to minus omega square r en cap plus alpha r et cap. The acceleration has two components as derived here. The acceleration component towards tangent to circle is called tangential acceleration, and the acceleration component towards the center is called centripetal acceleration. Now let's define about the uniform circular motion. The circular motion of a particle with constant speed is called uniform circular motion. In uniform circular motion, the tangential component of acceleration remains 0. The acceleration of the particle stays towards center. So we can write the vector v as v et cap, and the tangential acceleration is dv by dt. So this will be equal to minus a en cap. where A is the V square divided by R. The velocity of particle is changing its direction at every moment, but the magnitude of velocity is constant. The acceleration which is responsible for change in direction of velocity vector is called centripetal acceleration. This acceleration direction is towards the center of the circle. It makes a right angle with the velocity vector whose direction is tangential to the circle. Non-uniform circular motion. If the speed of particle executing circular motion varies, the circular motion is called non-uniform circular motion. In non-uniform circular motion, the particle has both tangential and centripetal acceleration. The tangential component of acceleration is responsible for change in magnitude of velocity, while normal component is responsible for change in direction of velocity vector. So we can write the vector acceleration equals at t cap plus an n cap, where t cap is a unit vector along tangent direction and n cap is a unit vector in the radially inward direction towards the center. So we get the radial acceleration as an equals minus b square divided by r, and tangential acceleration at equals dv divided by dt, which equals to r d omega by dt, which equals to r alpha. One correction is needed here, which is the vector unit vector n cap is towards the radially outward of the circle. Dynamics of circular motion. Using Newton's second law, we can evaluate the force acting on a particle executing circular motion. So, the vector force will be equal to mass times vector acceleration. If we write the equation in component form in tangential and normal direction, similar to acceleration, the force will have tangential and normal component, and we can write vector F equals Ft t cap plus Fn n cap, where Fn is minus mv square divided by r and Ft is m dv by dt. Banking of roads. Roads are banked with some inclination at the turns to reduce the frictional force on tire to zero. Let's consider the forces in horizontal and vertical direction. The forces acting on the vehicle are normal and the gravitational force mg. Let's write the force equation. So for this we resolve the normal force in vertically upward and towards the center direction. So the vertically upward component will be equal to n cos theta, and towards center direction n sin theta. So we can equate n cos theta to mg, and in horizontal direction n sin theta equals mv square divided by radius of the circle. So if we divide the equation 2 by equation 1, we can get the angle tan theta, which is the inclination of the road, equals v square divided by rg. Centrifugal force. Newton's law of motion cannot be applied directly while observing the motion of a body from non-inertial frame of reference. In such cases, a pseudo-force in the direction opposite to the direction of acceleration of non-inertial reference frame needs to be considered. Similarly, if the motion of an object executing circular motion is observed from a rotating frame rotating with same angular velocity as that of object, a pseudo-force is considered to be acting on the body in the direction opposite to the direction of acceleration of rotating frame of reference. For an object executing uniform circular motion in inertial frame of reference, the acceleration of the object is towards the center of circle. The force which is responsible for the acceleration is called centripetal force. We write the dynamic equation of motion as F equals m omega square r. If we observe the motion of this object from a rotating frame of reference, rotating with angular velocity omega, the pseudo force of magnitude F naught equals m omega square r needed to be considered. This force is called centrifugal force. It always acts in the direction opposite to the direction of centripetal acceleration of rotating frame of reference. Radius of curvature. The curve C shown in the figure has equation y equals fx. Consider infinitesimal small arc PQ of length ds, which is part of a circle with center, origin and radius r. The arc length is making an angle d theta at the center such that the arc length ds equals r d theta. Let's call this as equation 1. Again we know that the length of the arc ds equals square root of dx square plus dy square, and the slope of the curve at the point P is tan theta equals dy upon dx. So if we differentiate this equation, we will get sec square theta d theta equals d2y by dx square dx, or d theta equals 1 by 1 plus dy by dx whole square multiplied by d2y by dx square dx. Let's call this as equation 2. From equation 1 and 2, we can write radius of curvature r equals ds divided by d theta, and we know the value of ds from here and the value of d theta from equation 2. So if you put the value of ds and d theta, we will get square root of dx square plus dy square divided by 1 plus 1 plus dy by dx whole square multiplied by d2y by dx square dx. On simplification, we will get 1 plus dy by dx whole square whole to the power 3 by 2 divided by d2y by dx square, which is the expression for the radius of curvature. Let's solve a question based on the circular motion. A point traversed half a circle of radius r equals 160 cm during time interval tau equals 10 seconds. Calculate the following quantities averaged over that time. A. The mean velocity. B. The modulus of the mean velocity vector. C. The modulus of mean vector of the total acceleration if the point moved with constant tangential acceleration. The given parameters are the radius equals 160 cm and total time duration tau equals 10 seconds. So let's solve the part A of the question. Mean velocity will be equal to distance covered divided by total time elapsed. The distance covered by the particle is half circle, which is pi r, divided by total time duration is tau. So this will be equal to pi multiplied by 160 divided by 10 centimeter per second, which equals to 50.24 centimeter per second. Now let's solve the part B of the problem, which is modulus of mean velocity vector. The modulus of mean velocity vector will be modulus of displacement divided by time, which will be equal to the modulus of displacement is 2r and divided by tau. If you put the value of r and tau, we will get 2 multiplied by 160 divided by 10 centimeter per second, which equals 32 centimeter per second. Now let's solve the part C of the problem, where it is asked to evaluate the modulus of mean acceleration vector considering the tangential acceleration to be constant. So let's assume the initial velocity of the particle to be v naught j cap and tangential acceleration, which is constant, is wt. The final velocity of the particle will be v equals minus of v naught plus wt tau j cap. The mean acceleration vector will be W average equals final velocity minus initial velocity divided by the total time duration tau, which will be equal to minus v naught plus wt tau j cap minus v naught j cap divided by tau, which will be equal to minus 2 v naught minus wt tau j cap divided by tau. Let's call this as equation 1. The mean velocity is obtained by averaging the velocity at any instant of time t. So the velocity at an instant of time t will be v naught plus wtt, and if we average this using the standard formula, we integrate this velocity expression with respect to time and we will divide by total time duration. So we will get v naught tau plus wt integral 0 to tau t dt divided by tau, which will be equal to v naught plus wt tau divided by 2. But considering the distance covered, we get the mean velocity as pi r divided by tau. So let's equate the values of mean velocity in the both equation. So we will get the equation v naught plus wt tau by 2 equals pi r divided by tau, or the acceleration wt will be 2 times pi r minus v naught tau divided by tau square. From 1, the modulus of mean acceleration vector will be the modulus of w, which equals 2 v naught divided by tau plus wt. On putting the value of wt, which is obtained here, we will get 2 v naught divided by tau plus 2 pi r divided by tau square minus 2 v naught divided by tau, which will be equal to 2 pi r divided by tau square. If we put the value of r and tau, we will get 10 centimeter per second square. So this is how we solve this question of the motion along a circle. Now let's solve the second question. A radius vector of a particle varies with time t as r equals at multiplied by 1 minus alpha t, where a is a constant vector and alpha is a positive factor. Find a, the velocity vector v and acceleration vector w of the particle as a function of time. B, the time interval delta t taken by the particle to return to initial points and distance as covered during that time. Solution. The radius vector is at multiplied by 1 minus alpha t. So the velocity of the particle will be the time differential of this radius vector. So vector v will be a multiplied by 1 minus 2 alpha t. The acceleration of particle will be obtained by differentiating the expression of velocity. So if we differentiate the velocity with time, we will get minus 2 alpha a as the acceleration of the particle. Let's solve the part B of the question. In part B, it is asked to obtain the time duration delta t taken by the particle to return to its initial position. So for this, we will equate the value of vector r to 0 and we will get two value of t. The first value t equals 0 is corresponds to the initial point of the particle, and the second value, which is t equals 1 by alpha, corresponds to the time after which it returns again to its initial points. So the answer will be t equals 1 by alpha, or delta t equals 1 by alpha. Now let's evaluate the distance traveled during the whole time of motion. The distance s equals integral 0 to t modulus of vector v dt. So let's evaluate the modulus of vector v. So we will take the modulus of a multiplied by 1 minus 2 alpha t. In the time duration 0 to 1 by 2 alpha, the modulus will be equal to a multiplied by 1 minus 2 alpha t, and in the time duration 1 by 2 alpha to 1 by alpha, the modulus of vector v will be a times 2 alpha t minus 1. So now let's integrate these two expressions. So we will integrate the modulus of velocity vector v with respect to dt in the time duration 0 to t, where t is 1 by alpha. So this will be equal to integral a minus 2 alpha t dt from 0 to 1 by 2 alpha plus integral 2 alpha at minus a dt 1 by 2 alpha to 1 by alpha. On integration, we get at minus alpha at square with limits 0 to 1 by 2 alpha plus alpha at square minus at with limits 1 by 2 alpha to 1 by alpha. If we put the limits, we will get the expression as a by 4 alpha minus 0 plus 0 minus of minus a by 4 alpha. On simplifying this expression, we will get the total distance covered as a by 2 alpha.